All right, here we are with our lecture of about what is science. This is the second part. Um, we've looked at what is science and scientific methods. We're now going to look at an example of how you might go about doing an experiment and creating a hypothesis. And again, this is just a made up example, but uh, I think it'll illustrate some of the problems when doing science and using the scientific method. You may, it, Using these techniques may lead you to make some conclusions that certainly are correct, but you have to be careful about generalizing them uh, to every situation and being able to say that they are always correct, and almost nothing is always the case. In other words, whenever you say, whenever the sun is in the sky, it isn't raining. Well, that's not always correct. There are obviously the cloud that's producing the rain may not be directly blocking the sun, and it obviously can rain when the sun is out. So you can't make that assumption that those events always occur together. So let's take this example. I'm going to say that in my example right here, all right, let's go on and kind of like, we'll call this maybe, let's see, I'm going to just make something up simple here and say I'm going to hit my leg with a stick. Sounds kind of like simple, but let's talk about it. So when I hit my leg with a stick, all right, there is pain. So let's make something like a little arrow here. And I can say that, hey, that happens every time. I take my stick and I hit my leg with it, there is pain. And this is going to be my theory, and I'm going to say that this always happens. And so my hypothesis is that maybe injury or whatever, or a certain amount of force uh, applied to my leg causes me to feel pain. And this is very, very true. I mean, that's a great hypothesis. I'm pretty sure I would jump on board with that idea and say, yes, you are correct, that this is the case, that if I take a stick and I hit my leg with it, pain will be produced. However, is it always the case? So let's say I start doing experiments and I pull out a stick and I start hitting my leg, and yes, there's pain. So I mark it down. I start collecting data, and I do it 10 times, and all 10 times there are pain. And then I publish this and say, whenever you hit your leg with a stick, there's pain. Well, someone else comes along and says, we don't believe this. And we're going to do more extensive studies. And they also start hitting their legs with sticks. They get more and more people to do it. And they also do it for a longer period of time. So let's say you hit your leg with a stick, and they don't just do it 10 times, they do it 100 times. And let's say around 50, after hitting your leg with a stick 50 times, people begin to report that they no longer feel pain. It becomes numb. So now my theory is in question, that they say, no, this is not the case. Hitting your leg with a stick does not always cause pain. Uh, it only causes pain for the first 50 hits. So now we have to amend our theory to our new idea that something is causing the pain to subside. So we can say it this way: the original theory The original hypothesis, if you like, is that hitting your leg with a stick causes pain. Uh, but now uh, we have to do what we call amend it to before 50 hits. All right, we have to add that on. All right, we didn't anticipate this being the case, but of course, after 50 hits, your brain starts to block it. You release certain chemicals to reduce the pain, and it's like a natural painkiller. Endorphins and some other chemicals in your brain are released, and your brain begins to ignore the pain after a while. And so, after 50 hits, there is no pain. So now we have to uh, come up with new ideas, and of course, what happens is we have to add um, additional information uh, to our hypothesis and theories. Right? You only feel pain, of course, if there are not uh, painkillers present. Um, and so, no, you do not always feel pain when you hit your leg with a stick. Now, this is a very simplistic theory, but this is exactly how science progresses. Usually, you observe something in the world and you do some experiments, and it confirms your ideas, and you publish your work. You go out there and tell everybody, hey, I've discovered that when you hit your leg with a stick, it hurts. And I've done experiments, and those experiments have confirmed my ideas. And someone else comes along, though, and observes something slightly different. They replicate your research, and then they maybe add some additional um, variables uh, to the what do you want to call it, to the research, to the experiments, and throw in some different situations. Like in this particular case, they added additional hits, and sure enough, after a while, you didn't feel pain. And this is why sometimes in science it can be very confusing for people who are not uh, used to how science is done, because like in 19, let's say 90, you're you're young, and you hear about this new type of research, and something that makes you lose weight, or it aids in curing cancer or preventing cancer or something, and you go, okay, that's science, and that's proven, and that's what I believe. I believe that because they said that when I was young. And then 10 years later, they change it and they go, well, that's only true in some of these cases. Or maybe that's not true at all. Maybe it actually works a different way. We had it wrong. And they learn something else. And they go, well, okay, they got it wrong. I'll change my view to this new one. And then another 10 years comes along, and suddenly they're changing it back to the old one, or they're adding things. And the problem is the public doesn't understand what's going on. It's kind of like hitting my leg with a stick story. This complicates things for the public, and it's very important right now because there's a lot of what we call, bad science out there, and it does exist. But there's a lot of good science, and sometimes the good science, because as we learn more, we have to add on to our theory. It gets confused with some of the people who are doing bad research and sometimes intentionally trying to mislead you. And the public gets disillusioned with science in general and stops paying attention to it. Or they just believe what they want to believe. They'll pick the theories that they want to believe, and they'll ignore others. And this, of course, has been very true during COVID, and you get lots of crazy ideas, and they get repeated, which have no scientific basis whatsoever. But it depends on who's telling you about it. Uh, and sometimes the people who are the most qualified get it wrong. But that's to be expected occasionally. Um, and because science is changing and we don't know a lot of times, it's like the stick. Yeah, it works the first 10 hits, you feel pain. But after you get up to a higher number of hits, people begin to get numb to the pain. And maybe the next theory here, I have 50 hits. Their theory is it takes 50 hits. Well, of course, it's going to be different for different people. So the next researcher that comes along will explain that, well, you shouldn't have said it was 50 hits. You should have said it varies with the individual, and they instead change 50 hits to a range between, say, 30 to 70 hits. And somewhere in that range is when you begin to lose feeling. And then the next researcher after that will come in and classify people and say, well, it depends on whether or not they are in this condition or this condition that they will feel numbness. Are they tired? Are they rested? Do they have this particular gene or do they have that particular gene? And that all affects whether, when, and at, that they will begin to lose feeling and not feel the pain. So this is a simple example, but it's exactly how science works. And unfortunately, it leads to a lot of people just they stop believing in science and just decide to believe in whatever they want, or pick the pieces that they want. But over time, if the researchers are sticking to good scientific methodology, using the scientific method, using induction and deduction, you will eventually come to what is, a reasonable, what do you want to call it, theory that is quite what we call robust. It can withstand a lot of testing and always get the same answer. Now, this is easier in some fields than others. Physics, it's very easy to replicate. I shouldn't say easy, but there are fewer variables to disrupt your experiment. So physics is considered what we call the hardest science. So I'm going to move down here and begin to define hard and soft science. And it depends on hard and soft. Hard sciences are the sciences where it's easy to replicate the experiment and get the exact same answer every time. So generally we represent hard sciences as the ones that easier to replicate experiments. And the best case, chemistry and physics. All right, so let's say chemistry. These are the easiest and the hardest sciences they're the easiest to replicate the experiments. So someone does an experiment, another person tries it, and they get the same exact results. That's going to indicate that you're in a hard science. Oh, physics. All right. Now, there are softer sciences. Biology is increasingly a hard science as we apply more and more chemistry and physics to our experiments. In other words, biology builds upon what is learned in chemistry and physics. Very true. We learned how lenses work and improve microscopes so that now we can see more details inside of a cell, for instance. That's something that comes from physics that allows us to improve our experiments in biology. We learn how chemistry works, and we apply those chemical processes to biology, and we learn, again, how the cells work. So the idea that biology builds upon the base of chemistry and physics is very true, and it's currently making biology a much harder science than it used to be. Now, there are also the soft sciences. Oops. And they have a harder time doing experiments. They often have um, have have to do experiments that are simply observational or statistical. Observational. There we go. And in fact, we wouldn't call that an experiment. I misspoke here. They have to do just research. All right, that is simply observational, and it's at this point it's not really science. Um, just doing statistical research is just essentially observing. When you can't do experiments or can't easily do experiments that you can replicate and get the same answer, you move into the soft sciences. Let's see, observation. Let me get this spelled right. All right, observational. When you do this, and some of these are uh, things like psychology or sociology. These are softer sciences, not considered hard sciences, because you observe people, you ask them how they feel, and asking someone how they feel is not a directly controllable measurement. So you just can't use the same. Uh, uh, it's not the same as something that you've measured in the physical world. You've gone through somebody's interpretation of the world, and therefore it softens the scientific accuracy of the research. So, good examples of these types of softer sciences, as we call them, all right, might be psychology or economics. And in fact, you can do hard science in microeconomics. If you know the difference between micro and macro, microeconomics are actually quite good, their scientific research. But macroeconomics, where you study large groups of people or nations or huge corporations, unfortunately, you can't do experiments on them. You can't tell a corporation, oh, we think you ought to fire half of your workforce so we can figure out if this is good for you or not. No, they're not going to do that. And you can't tell the Federal Reserve, the government, to say, why don't you lower taxes or raise taxes, or why don't you spend money on this particular thing or stop spending money on this particular thing, and let's see what happens. Well, they're not going to do those experiments just because you want to, uh, because it affects so many, millions of people, literally. Uh, they're just not going to do those experiments. They're going to go by their theory, and but their theory is not based in experiments. No one's ever done the experiments. It's all observational, and when they've seen this occur in the past, they've said, "Oh, look what happened. When these things happen, we think it works this way." But nobody has ever done experiments in macroeconomics, so that's why economists get things wrong so easily. It's because they can't do experiments, and it's similar in psychology. You do some experiments, and the part of psychology that is probably the most scientific and pretty good is when it can relate it to biology. So they've learned how the brain works, and it's not just observational now. Uh, they can do biological experiments on animals, and therefore they can then say this probably works the same way in humans. And so psychology has become, at least when it's linked to biology and chemistry, quite scientific. Uh, but the other aspects of psychology, where it isn't linked to biology, much less scientific, and we definitely call that a soft science, as is economics, because they simply do observations. They can't do experiments. So our definition of hard and soft science is going to be how easy is it to do experiments in your field. If it's easy to do experiments like chemistry, physics, and to a great extent biology, it's a hard science. Uh, it gets softer when you get to some parts of biology, and then it gets very soft when you get to psychology and economics. So those are not considered actual true sciences. And in fact, to give you a story about this, Darwin, here's a question to ask yourself: was Darwin a scientist? And in fact, let's put a question mark by that. Did he do experiments? And the answer is no. It was all observational. So therefore, you really couldn't call him a hard scientist, maybe soft, but his everything he did was observational. So he just watched things and tried to come up with theories on why these things occurred. So, in fact, he is considered something called a natural historian. Not, well, I was going to capitalize that. All right. A biologist. In fact, really, biology had not become a true field. You did not go to school to get a biology degree in his day. And there was no going to get a degree. It might have been one or two places you could go. But what he did was generally called natural history. And natural history, today we would think of a natural historian as like a bird watcher or a butterfly collector. And so Darwin was a natural historian. There really wasn't such a thing as a biologist. There were medical physiologists and people who were doing medicine that was very close to what we call biology today. But nobody was doing exactly what we do today as biologists. They were more like medical doctors than they were biologists at the time. They were interested in anatomy, and they were interested in how the body worked, but they weren't quite biologists. And the natural historians had not yet added the scientific method experiments to their work. So at the time of Darwin, he was a natural historian. He was not really a biologist. We would call him a biologist today, but generally you need to do experiments to do hard science, and that is the goal of biology, is to become as hard of a science as possible. And to do that, we borrow from chemistry and physics. All right, now we're going to move on here to the last part of this part, is the relationship between technology and science. So how does this work? What is technology? Technology, you can think of technology are the tools. Tools to observe and manipulate the world, the universe around you, the environment. Manipulate, that means, change. Environment. There we go. So in other words, a pencil is a tool. You don't necessarily observe it, but you manipulate the world. You move graphite from the tip of your pencil onto the paper. You have manipulated the world. You've changed it. A rock is a tool. You use it to do something, to accomplish a goal or a task, and to manipulate the world around you. You can also use it to observe or better observe the world. You invent magnifying glasses, and then telescopes and microscopes, and those are technologies to help you observe the world around you. So tools or technology help you interact with the world in more complex ways. So you could use my simple one here to observe and manipulate, but you could say to interact instead of just observe and manipulate. You could say interact with your environment. Now the thing is, there is a relationship between technology and science. That technology uh, is one where you have a tool and you invent a new tool like a microscope or a lens. Tools, all right, lead to better observations, and we've already seen that's part of science. You're improved. You can see smaller things or more distant things. For instance, that would be the invention of something that allows you to um, understand the environment better by seeing smaller details, etc. So tools lead to better observations and more complex manipulations. All right, that means you can alter things maybe at a tinier scale, for instance, or more subtle ways, maybe chemically instead of just physically. So you want to alter something, and normally you have to hit it with a hammer. And so, well, maybe there's a different way to manipulate this material. Maybe we can pour acid on it. So the that's a tool. Chemicals are tools to manipulate. And I'm going to say the world here just to save some spell, but I mean the environment, the world around you. Oop. It's not going to be nice. I wanted to. Yep, my word processor isn't going to be nice. I'm going to put spaces in there. Hold on just a second. Keep this looking reasonably. No, I'll leave it like that for now. I'll go back and change it later. But this is the idea that you want technology in order to improve your observations and your manipulations. Well, when you do that, you learn more and you come up with new theories. So you have the idea is that technology leads to better science. And then once you have your theories, science involves the theories and you figure out how it works. And once you know how something works, you can devise better tools. All right. So you make better tools once you have a theory about how things work. And of course, that in turn leads to better science. So there is a constant improvement with science and technology. They interact with one another in cycles. So you learn to manipulate the world a little better or observe the world a little better by inventing some tool. This lets you learn more about the world and you come up with better theories. And with the better theories about how things actually work, you devise better tools. And then once you devise the better tools, therefore improve science even more. So there is this cycle of tool invention and improvements in science, and then again back to better tool invention. And this is the interaction between technology and science. They really do work well together, and they're what we call progress, at least scientific progress. Progress is the result, as we call it. At least scientific progress. There might be other types of progress, but certainly scientific progress is the result of the interaction between technology and scientific endeavors, scientific research. All right, and that will do it for Chapter 1. These are, like I said, my own personal lectures. They're similar to the topics in the book. I will also do lectures involving the PowerPoints which directly are associated with the book. They're similar to this, but they are not the same. This is the more important information than what's in the book. We follow along with the book. You will be tested on what's in the book, but if you have a limited amount of time and you're going to only study 2 hours instead of 6 hours, you would be better off studying this material first, and then the details that are in the PowerPoint lectures. So these lectures, as I say, should be your first run through and when studying, and then once you think you've got most of this information down, I would then move to the PowerPoint lectures, which are more directly related to the book. And then once you've kind of run through those, then you might go ahead and read the book. And I am well aware that most people don't read the book. The book reading is left for the people who want, a 95. You can probably get away and even make an A without reading the book. From what students have told me, they say, well, we listen to your lectures that you do in class, which is like this. Then we review the PowerPoints, and a lot of students say that's usually enough. And then there are those who are really gung-ho, and they go ahead and go through the book. And there are reasons to go ahead and read the book. You get what we call contextual information. A different person explaining something, I explain it a certain way. PowerPoints explain it a little bit. But when you go back and read the book, you've got all those fine details that can be helpful in answering the questions. And there will be questions that are directly from the book. Usually in my class, I try not to tell you exactly what parts you need to look at and what parts are the most important. And by far, these lectures are the most important. All right, and that'll do it for Chapter 1 notes lectures. This is, like I said, the kind of lectures you have in class where I would be writing on the board.